Thank you, Mark. It's honor for me to be here to give you the presentation. I come from Xi'an. That's the first time for me to give a presentation here. And the first is introduction to my lab. The name is Cyber-Physical Detection Lab. I was in a school. I'm in the School of Mechanical Engineering, Northwestern Polytechnic University here. And in Chinese, my name is Weiping He. That is Chinese character. Why I show the Chinese character? Because the story of the lab begins by the city and by the university. That is here. Is in the the northwestern of China, but in geometrical it should be in the center of China. Xi'an is the capital of 13 dynasty in ancient China, so very ancient city. And the university is in the top 15 to top 13 in China, the university. And the top 5 in School of Mechanical Engineering in China. And aircraft manufacturing engineering top 1 in China. And industrial design top 6 in China. That is our school and our department. Here is.
I'm sorry, people are having a little bit hard time hearing online. I wonder if you can sit here and, and then you're in front of the microphone.
Thank you.
That'll be great, and then you can use the laptop there. So that's okay.
Yeah. I should use that?
Yeah, use this one, but you'll also use the microphone here, so it'll be
okay.
Good. Okay.
Maybe here?
Yeah.
Thank you, Mark. That is most famous technical driver in Xi'an. And this is the new campus of our university. That is the School of Mechanical Engineering in old campus in our city, in our university. And you see this one? In the center of the new campus, we have a sculpture. The name is He. You can see it's a cup of wine. In the inner of the cup, we have 3 Chinese characters. 在之中国. It says I should reside in the center of the land. That means this is the 中国, the first appears in history in China, and 中国 is the Chinese called China. We say your nation is 中国. So our university has this sculpture in the new campus, and we say the center of China, we believe, is just in the new campus, the position in the new campus. So we build this sculpture in our new campus. Okay, that is the original of the term 中国. Next, the story is the He is found in Baoji city, 150 kilometers away in the west of Xi'an city. That is a new campus located in Xi'an, and the 150 kilometers west is Baoji City. We found this Hezun. And next 150 kilometers west is another city named Tianshui. That is another city that is I born in Tianshui. And you can find the character, you see the Hezun, white Hezun, because a worker, his surname is He, made this artifact. That's just the name of my family name. That is very interesting. And in ancient, in Chinese ancient mythology, we think Fuxi and Yuwa was the first ancestor of Chinese civilization, the first man and woman that born in Tianshui city. That is the first civilization, the first ancestor of Chinese civilization. They have a pair of compass in Yuwa's hand and a triangle ruler in Fuxi's hand. Not only they have the man and woman, also they made the rulers for the civilization of China. And what's before? In Chinese, the beginning of the world is chaos. And a man named is Pan Gu cut the chaos and create the sky and earth. The air up to form the sky, and the dust goes down from the earth. And we say the sky is round, the earth is square. That is Chinese civilization, the beginning. And we also have a temple for Fuxi in Tianshui. Every year we have a great and it should be celebration for the birth of Fuxi in Tianshui. That is the story about our university and about this Hezun. That's a small copy of that artifact. Okay. Now begin. That's a story, and I begin my academic story. We see that the beginning of the world is chaos, and Pan creates the world, and Fuxi Yuwa established the cosmic order of the world. Fuxi creates only the physical world. We say before the age of digital and AI, we have a pre-agricultural era, agricultural age, and industrial age. In that time, who are the creators? We say the human beings. By what we advanced and scientific and social progress, we say we use natural language text and drawings. We record all our progress on papers and books. That is before the age of digital and AI age. And now I have this. Who are the creators? They are human beings, and we have AI. And by XR, interactions can first break the limitations in the physical world. We can see the digital space and AI breaks the law of physical. We abide by the physical law, but we can across the limitations of the physical laws. That is why we can do more than before. That is, we can traveling through the space and the time. The second, we can face the interaction can face the digital and the physical realities simultaneously. That is only in case we can see the digital world and the physical world. We can span in the physical and the digital world and do a lot of things. Third, we can treat the digital and the physical realities equally in a parallel universe. In most cases, AI can do a lot of things in that case, but because of the time limitation, today I only focus on the digital part of the changes. I have such diagram. That is the physical world. That is the digital world. I see the cyber world is connected to the name of our cyber physical interaction lab. And we have human, we have AI, and in each part I show some important areas in this picture. Actually, all the I see all the knowledges I expressed, and next actually are the results of the change. I have a lot of papers which are published last almost 10 years, and to show all the researches according to these three parts of knowledge. And today's is fortunate that today's topic is haptic. I think haptics is a very good topic, and we can do a lot of things, and we can make a very good papers. It should be better for the students. This one is in a study. We break the limitations between the physical world and the digital world. So slowly.
What is happening? Did you click on the play on the thing?
Oh. Maybe that is the beginning.
Yeah. There we go. Perfect. There we go.
Yeah. In this video, we say in VR situation, if you put on your VR headset, you enter the digital world. You cannot see the physical world. If you get a phone call, you have to put off your VR headset and to process your phone. But in this picture, you can see you can interaction with the physical objects in digital space. He operates his smartphone in VR and process the stuff in physical world. That is, the XR interaction inhibits the dividing between the digital and the physical world, breaks the spatial temporal constraints, and expands the operational space. Actually, we have a camera here to detect the finger, and we process the smartphone. We send a message. Okay. He have not took off his VR headset. That is one. Next is sketching in VR. With sketching AR, we have no haptic feelings, no tactic feedback. And in that case, you will not draw the line maybe you do not like. That is our solution. Why? You should be sound.
Huh. Yeah, I don't know why. There was sound before.
Maybe it's a delay or something. Oh, let's begin. We have a tablet which can input the 2D line and the curve, but it gives the feedback in this world. But if you draw headset, VR headset, if you're drawing a line on touch, just in the air. If you hold the tablet, you can show it in the tablet. You can get a feedback, not that accurate, but you get some text feedback. If you show the tablet as a cup with a handle, much close to the real cup. When you hold the cap, and if you use the cap, you hold the cap and draw the line. It looks more realistic. That's the feedback, fusion the vision and the feedback of haptic by your brain.
So this is a very nice example of passive haptics, where you're holding a curved cup object that you're drawing on a flat surface, and it maps onto the curve, so it has also the perceptual illusion. So passive haptics plus the perceptual illusion.
It is more something like this. Oh, it is perhaps the same one. Oh, the same one. I should go to the next. After that, we also built a whole tab sketch system. Something like this. you can see everything is in digital world, but you can hold your objects to drawing the pictures. Another one. That is the last one is something for design, product design. This one is for manufacturing, for assembling. Here we also need to process assembling in VR space, in digital world. But if you if you assembly a part to another one, we have a part touch, and we have a support. If you have some parts to set another one, we have a support. In the VR world, we doesn't have the such haptic touch, and we do not have such support, the physical support. We only put that position, it can hold in the air. But if you operate it in real world, you have to the touch, you have to get the support for each part of the assembly. What we do is that we have two end effectors. One is the support, another is the part you want to assemble to. And the end effector is on a robot. The robot moves and turns to the exact position of each process for the assembly. It can change the position, change the direction. Thus, we can make the part-to-part touch, surface to surface, plane to plane, and hole to a cylinder. So the end effects of both these parts, we have a cylinder, we have a hole, we have planes to get a position, right position. And the real position for the touch is by the robot arm. Let me see. Maybe it does not have sound.
Yeah,
So
I don't think it needs a sound. I think it's okay. Yeah. So this is a very nice example of having a robot that can move the passive plane into different areas. So as you touch different shaped physical objects,
yeah.
the robot rotates around and puts a flat plane or a curved surface or whatever the surface is that you're touching. So you can see
the operators or processor assembly in VR world, in digital world, and he can get the haptic feedback and even have the support of the digital object to digital object. Next, in this, that we see we use what I see we use proxy. What's something.
Yeah, haptic proxies.
We have a tangible proxy, but proxy is for the haptic feedback. In vision, that is a difference. So this study, we also have some enhancement for vision and haptic. So we have a visual relocationization. That is, if you in physical, the bottom is here. In vision is here. So if you touch the bottom, but you can see the difference. Actually, they're not necessarily the same. So in vision, we can do some enhancement, relocation, to get more realist feedback of touch. There's some more algorithms for the touch. You see, the proxies are, it's a circle. The real object is more much expanded, complexity. Then we can we can do some relocation to the fingers in vision. There's some precise feedback. This one is for, we discover the difference between the, we do some research. We can find the difference which is due in the physical world, and another one is in the digital world. We are study what is the difference. That is another paper. This is not for haptic. This for just for vision.
In real offices, physical displays are often limited by space and cost constraints. AR devices make it easy to create and adjust virtual displays. In his first viewpoint, there are two translucent monitors. AR interfaces can be simulated through MR. When users work outdoors with AR, the surrounding environment is dynamic. This creates difficulties for the designer or researcher. MR was used in scenarios including city navigation, firefighting, natural disasters, and surgery. In this work, we focus with exploring the effectiveness of MR simulations of office tasks. We designed MRSS to simulate a real AR office. We designed 4 typical office tasks for the user study. We conducted user study in both indoor and outdoor conditions. EEG, task performance, SUS, and NASA TLX questionnaires. Results of interviews are synthesized. When using the MRSS, participants confirmed fingertip position through a pass-through window, resulting in reduced performance, increased cognitive load.
You put the place in the bridge above a street.
And when there is little reliance on keyboards, AR and MRSS are only problematic in terms of physical demands, workload, and attention. Significant difference test and equivalence test were performed on the results. The typing speed of AR in indoor condition was significantly higher than that of MRSS. The number of backspaces was significantly less than that of MRSS. The drawing complete time was significantly higher than that of MRSS. The equivalence test shows that the backspace number of AR under indoor conditions is not equivalent to that of MRSS. There was no significant difference between the MRSS and AR on the total SUS score. Both tests point to a significant increase in physical demand under MRSS.
Next one is also assembly. It's blind area assembly.
Exploring the core cognitive dynamics of MR enabled in situ assembly visualization. In assembly work, there are numerous blind areas caused by obstructions. Workers' blind operation has led to decreased efficiency and increased errors. In our work, we set up a simplified blind assembly scenario where the task was to insert bolts on 3 sides of a cube. Compared to guidance from paper documents, mixed reality visualization can provide intuitive guidance to assist assembly. However, due to the limitations of current equipment performance, it is currently difficult to fully track scenes and parts. The movement of hands and parts is difficult to track completely. We propose a method that integrates force and pressure sensors with an IMD, employing an open gun architecture blind zone configuration to simulate future advanced visualization systems. In this way, we have a fake blind area assembly visualization system to try out future advanced performance. Building on this, we conducted a user study to explore the core cognitive dynamics of visualization. We used E to monitor the user as cognitive state and divided the operator as actions of pick gun up, localization, and insertion the bolts into 3 stages and 3 triggering actions. First, we analyzed the results from SUS, NASA and task performance metrics. The MR visualization system demonstrated outstanding performance across all metrics, proving that it successfully simulates future systems. POS analysis demonstrated reduced cognitive load across all stages compared to the blind assembly task. The visual stimulus increased while decreasing demands on cognitive resources such as working memory and attention. The EOH results revealed reduced connectivity in sub-regions under beta, theta, and alpha bands, while other frequency bands demonstrated significant enhancement. In ear-pit analysis, baseline conditions revealed prolonged OT on-off and 2, P2, and P3 component, demonstrating that MR visual feedback accelerated cognitive processing, enabling participants to evaluate stimuli and make decisions more efficiently. After a comprehensive discussion of both scenarios, the conclusion is reached that blind area assembly is a movement involving the integration of motor imagery and tactile sensation. MR visualization significantly enhances the process through visual feedback, providing stronger visual stimulation via virtual models. Based on the results, we envision the current technical bottlenecks of MR visualization system met OT on and next development path. Thanks for watching.
That's her result. Actually, we have a lot of such papers. That's some, we can see some typical results of, I see, back to the, sorry. Yeah. yeah, the logic for the research. And in conclusion, I hear. Sorry. Oh,
you stop sharing. You closed the application. You reopen the PowerPoint. Yeah.
No, I still have the PowerPoint. Actually, I still have
it's still on Zoom, but your PowerPoint slide is not here anymore.
I should share it again.
Yes, share it again. Yeah, share it on your computer. Yeah.
This one?
Yeah, and then just
share
at the bottom here.
Share.
And this is it this one here?
No.
I think you closed PowerPoint. You closed the presentation.
Oh, it's here.
Yeah, but where is the slide? Yeah, that's good.
But I
can't go down to the
Which one?
You have to make this. Go back to PowerPoint, and then put this into presenter mode. Yes, and then go back to the Zoom. So using the tab, Alt tab. Yeah. Yeah. And then do the screen share.
Screen share.
Yeah. Then share, and then
this one. It should be this one.
Oh, that should be. Yeah,
it's good.
Perfect. Yeah. Good job. That's great.
Sorry. The next part here of the research is emotion. Actually, we see if we treat digital world equal to the physical world, even though we can do nothing about the objects, physical objects like some parts, we can see a robot have some feelings and emotions. We do a research that is with physical emotion enhancement, which some 10 years ago, we can show you the result. The objects can have emotions using AR-based approaching. Object with a QR code, it can be touched by a computer. Really? You can see. Another one, it smiles or it's crying, it smiles. In that case, we can do some study about two ordinary objects have some feelings, have some emotions. We use the two objects have equal weight. There are tails and a smile. Have a different weight. They're crying. Now there is that. In industrial manufacturing, if two pairs of pass through the tails, we can show the smile. Otherwise, we show crying. This study 太超前了，所以 we have not processed 没有进一步进行这个研究。可以啊，行吧。Okay. The conclusion. The conclusion is something like this. The XI interaction break spatial temporal constraints, expand the interaction space, achieve the cyber-physical integration, expanding the operation behaviors, especially the multimodal interaction brain of human forces, cyber and physical. That's very important for the interaction, because interaction is the interaction between machine, object, and human. All the interaction is feelings about the brain. You can feel good and feel bad. It's your brain. And at last, my thank yous to Professor Mark Billinghurst.
Thank you.
I have all the papers here get help by Mark, and we have cooperated over 10 years, over 20 or 30.
More than 30, yeah, 30 publications.
Issued 30 papers, very high top journals paper we have achieved. That is very hot and very good area. Thank you very much.
Okay, thank you. Great, thank you so much for your presentation. That's fantastic. So that was a very nice survey of a lot of work he's done in the Physical Lab. You can see some of it is passive haptics and drawing on surfaces. So we have some time for questions now. Does anybody in the room have any questions? I had one question. So I really like the work with the robot being able to move the proxy around, so you can be touching. And so one thing that was maybe not clear from the videos, it did a very nice job of using the Quest controller to do the tracking. So you can have the Quest controller on the robot arm and the Quest controller on the physical object the person's holding to try and dock with the piece as well.
Yeah.
But I'm just wondering how you can scale that. So the surface you have right now is a quite small working volume. So how can you make that bigger? So for other types of tasks.
It depends the robot arm. If it is over the range of the robot arm, you cannot do that far, because the object in the VR, the position is controlled by the robot arm. So if you scale it to a big area, you should have a
big arm,
big arm. Or something you can more robots to control the proxy.
Yeah, that's a very good question. Yeah. Does anybody in the room have some questions? Anthony or Kai or Rob or Gunn, do you have any question?
I should have a question. First of all, what do you think of the future of human-robot interaction and haptically? How do you think we can use robots to interact with human haptically?
It's a very good question, and it's quite difficult for human to interact with the robot, because the robot's movement is easy to censor, but it's difficult to control the humans. It's very difficult for you to know how a human movement is very not by the brain, by some traditional or by some habit. So it's very difficult for you to see. If you shake hands, you shake hands, and you may do not use your brain. Just shake hands.
That's just automatic. So
automatic. It's difficult to. That is a very good question, and it's a very hard topic in robot-human interaction. And the difficulty is about 算力. You,
Algorithm.
yeah.
Computation power.
Yeah, it's about if your AI is powerful, they can guess you more accurate for a human's movement. That is easy. Otherwise, it's very difficult to get a smooth and good interaction.
Thank you.
Thank you. Does anybody have any other questions? He will be around a little bit today, and then of course tonight for the downtown you'll be able to see him as well, and also tomorrow as well. So yeah, but it's a very nice example of having some good collaboration. We first met more than 10 years ago, and we've been able to work on and off over the time, and I've been able to visit his lab and spend some time in Xi'an. It's really amazing, and we've been able to host some people from there here, and in fact one of my postdocs now in Auckland, Zhuang Chang, he was originally met him as an undergraduate student in his lab, and then he went all the way through and did a PhD with me in Auckland. First of all came as intern, did a PhD, and now is postdoc. So it's a good example of having nice international collaboration. So for those of you who are thinking of academic career, make sure you always say yes to people and try and connect internationally, because you don't know opportunities will come from that. So it's great.